So when it's in the air, it's dealing with gravity, which is 9.8 meters per second squared. But that squared tells us that we are dealing with quadratics. What's quadratics? It's that exponent 2. The actual equation is y equals ax squared plus bx plus c, and this equation forms this nice parabola. Let's see clearer now. Taking apart the equation, you have the variable a, which is the quadratic coefficient, because it directly influences the variable with the exponent. You have the linear coefficient b, which deals with just the flat-out variable, and you have the c constant, which is pretty much a starting height. And so to figure out what all these variables did for the whole equation, I decided to try to mess around with the numbers individually. So first, I messed with the quadratic coefficient and got rid of everything else in the equation. So you see y equals x squared, y equals negative x squared, and y equals negative 2x squared. And so the quadratic coefficient decides if the whole parabola is going to be facing up or down, and it also sort of decides how steep it's going to be. Like negative 2x squared is steeper than negative x squared, negative 1x squared. The linear coefficient does some kind of funky movements. X squared plus x moved the normal x squared equation a little bit left and down. X squared minus x plus negative x moved the entire thing right and down, and x squared minus 2x moved the entire thing farther right and farther down. So it just sort of moves it in this L shape like a knight in chess. When you change the constant, it just moves the whole thing up and down, x squared plus 1, minus 2, very straightforward. And so when you start changing all three at once, you end up with some pretty crazy curves going every which direction. This is really important for my actual project. It's solving for x-intercept, which is solving when that curve crosses the x-axis, which means because it's a parabola, you're going to have 2, or maybe sometimes you'll have 1 if the peak of the parabola is just hitting the x-axis, or you might have none if it never actually even touches it. But in my case, there are 2. So the way you do this is you make y equal to 0, which if you just have the y equals ax squared equation, then you could just replace y with 0, but sometimes you already have a value for y, so you need to sort of manipulate numbers. But you get y down to 0, and then you plug in your a, b, and c values into this lovely, simple equation. And the key to getting that 2 solutions is this plus or minus. You solve it one way plus, one way minus, and it gets you 2 numbers. So now, bringing it back to catapults. One weird thing about the movement through the air is that x and y, side to side and up and down, aren't related. You don't have an equation y equals x squared. It's actually, they both deal in time. And so side to side depends on the velocity of the ball, and the up-down depends on velocity and gravity. X and y don't matter, which is really, wow. To illustrate this, I have the equations. X has its own little equation, it's kind of cool. X has horizontal velocity times time, and y has 1/2 the force of gravity times time squared, plus vertical velocity times time, plus starting height. And if you'll notice, there's not even just one velocity, there's actually 3 that we're dealing with, which you find using this diagram. You first find the initial velocity of just whatever speed it gets fired from the catapult, and then you plug in the angle at which you're fired, because that's how you keep all your parabolas from looking the same when they're fired from the same speed. Because if you're launching it at 80 degrees, you would be launching like that. And so most of its velocity and energy is going to be focused on going up and not into distance. Whereas if you're launching it at 10 degrees, most of it's going side to side and not up. And that's what keeps, and so you're going to have different velocities for vertical and horizontal. And so you get to use some sine and cosine. So, for example, we have a initial speed of 7.7 meters per second and launching from 20 degrees. So we want to calculate how much speed is focused on going side to side and how much is going up and down. So we use sine opposite over hypotenuse to get that the vertical velocity is about 3 meters per second, and cosine to calculate that horizontal velocity is about 7 meters per second. So obviously, if you look at it, most of the energy is going side to side. Now we want to find out how long it'll be in the air, which means we want to solve the y equation for time. And if this looks familiar, it should, because we get to use this lovely equation now, which is when it comes in handy. And we just have to plug in all our simple numbers. It's completely simple. Time equals negative b plus or minus square root of b squared minus 4ac over 2a. It's perfectly simple. You just use order of operations, and when you've done all the math, you get that time will be at hitting the ground at negative 0.085 seconds or 0.623 seconds. And it also seems a little weird when you have a negative number for time, but it's actually okay, because if you look at the marble launcher, we're launching from 26 centimeters up, and we're already in the problem when it's launched. And this is finding when it's at the ground and at the ground. So it's this weird sort of negative time before it was ever launched. So it doesn't make sense in real life, but in math terms, it's completely okay.